Here's the other thing that surprised me, and it's the last piece of our puzzles we're going to get to before the end of today. QC frequency here decreased. We have the assumption that the methods are so much better, but look at that decrease in QC frequency. Is that justified? Well, let's go find out. Remember, the determination of the acceptability of residual risk of harm to the patient is based on an evaluation of the potential costs, both in terms of the patient's well-being and in terms of financial liability to the treating parties versus known benefits to the patient. So let's come over here. We had established earlier that we test 30,000 patients a month. Say the average cost of a medically unreliable result, I put it in at $50. So you can come in here, you can change the cost per test, you can change the dollars it costs to do the QC sample. What does it cost you to run the QC sample? And the only other number you can change is the QC frequency. When you come over here, you look that the medical director has set an acceptable risk level of 2.3%. We're going to choose to model a 5% failure. With lab QC, there will be 1,000 patients reported at a cost of $50,000, and you're spending $30 to control quality. With the mathematical process, there are 34 patients less than $2,000. The number of times that you run the QC determines the patients per run. So we have 1,000 patients per QC run, and we're taking 20 runs for a reject. In other words, this method is never ever going to detect a clinically significant failure. So there will be 20,000 patients at risk if this method fails. That means 66% or 66.7% of the patients every month would be exposed to unacceptable risk if you test it this way with a method that will never detect it, whereas if you do your QC with a method capable of detecting error and increase the QC frequency, you're maintaining that magical 2.3%. Let me go over that a little more slowly. Let's go back over here and now we're going to go back over here and we're going to pick a more reasonable QC rule. I'm going to put this down to, let's select a 2S rule. Whoops, just for the fun of it. Now, if I want to, now here's how it works, guys. If you really want to, if you care enough about that method, you go down, you crank your 1,2S to a reject. Now, are you able to detect your error immediately? Absolutely yes, and absolutely 1. So this will have even higher error detection than this. Now if I come over here to evaluate the risk, they both have 1 run to reject. The medical director set a value of 2.3%. Your observed value is 0.03% or 0.00%. The acceptable risk level is 2.3%. When you say I will accept the sigma of 2, the margin for error of 0, you're saying I'm willing to accept 683 bad patient results and absorb a cost of $34,000 for these results that can fail every month, and I'm not going to design a QC system that is going to detect them. The standard that's used in this scenario is 2.3%. If that is the standard, you are allowing 683 medically unreliable results at a cost of $34,000. If you do your QC this way, you're going to spend $2,500 as opposed to $1,700. The computer will sort out for you, is the risk acceptable? Is the risk not acceptable? And then you come in and say, is this risk acceptable to me? This is the mathematical calculation. Now you come in and say, okay, with what I know, I'm going to say it is or it is not acceptable. And if it's not acceptable, I have a series of choices. I'm going to assign the recent mean and SD on the chart if it is acceptable. I'm going to implement the optimized QC rule. I could increase the QC frequency. I could decrease the QC frequency. I could improve method accuracy, I could improve method precision, I could change the acceptable risk level, or I could change the medical goal. If you can't meet them, change them. So you can come down here and pick up to 3 things that you're going to do to improve the system. If you do more QC, you do get less risk.